Okay. The geometric distribution is kind of a spin-off of the binomial distribution. Right? So the conditions that need to be in place, I'll just put it to you this way. Everything is the same as the binomial distribution, except you don't have a fixed number of trials. Right? So you'll have a probability of success, you'll have two outcomes, you'll have independent events, but the number of trials will vary. All right? So that's what all of this is kind of boiling down to. And the idea is, you know, if you talk about, let's say, somebody taking free throws, and they're going to take 10 free throws, and their probability of success historically is 0.9. They make 90% of their free throws. If you watch basketball, you see that that's a thing. Like, he's a 90% free throw shooter, or she, you know. So there's that kind of question where you're going to take 10 shots. What's the probability of making all of them, none of them, half of them, at least two of them? You know, you can do all sorts of things with that. But then you have the case of, and you can kind of imagine you're watching a game and a person who normally is a 90% free throw shooter has just taken 5 shots and hasn't made any of them. Now you might be wondering, well, what's the probability that he could get through 5 shots without making any, and maybe the 6th shot is the first one that he makes? Right? That's the idea of a variable case, because sometimes going into a game like that, you have no idea when that person's going to make their first shot. You suspect it to be pretty soon if they're 90% free throw shooter. Maybe they're injured, maybe they're choke artists, you know, like big game, you know, NBA finals, and all of a sudden they've lost the ability. They get the yips, you know, that's another possibility. So you can ask yourself, well, what's the probability that he makes the first free throw on his first attempt, on the second attempt, on the third attempt, on the fourth attempt, and so on. All right. That's what a geometric distribution will account for. But the thing is, it's really infinite. I mean, practically it can't be, but in the sense that that person can keep taking free throws and never make one. You know, you only become interested when the individual makes their first free throw, but you don't know when that's going to happen. All right. The example I used here was rolling a die. So I just kind of broke it down in this table, just kind of, you know, cut to the chase. This is the number of attempts before first make. I was trying to think how to word that. Yeah, because attempts works even in the case of die. Before, I'll say first success. All right. So maybe the individual gets it on their first trial. This one's talking about rolling a die and getting, I forget, getting a 6. So 1 in 6 chance that that person will get it on their first try. Getting it on their second try means they didn't get it on the first try, which means that we have the probability of them not making it times the probability that they will make it. First attempt, second attempt. All right. It gets exponential in that regard because when you go for the third attempt, the fourth attempt, you're just going to keep multiplying by the probability of failure, and that will precede the one instance where you would multiply by the probability of success. All right. So if you're looking to generalize it, you know, you'd say, okay, well, on my second attempt, I have 5 over 6 to the first. I'll actually write it in a kind of a new setup here. I'll say 5 over 6, actually for the first one, to the 0th, right? Because every other product has a 5 over 6 in it, so why not throw it in here? 1/6. Then this one would be 5 over 6 to the first times 1/6. 5 over 6 to the second times 1/6. 5 over 6 to the third times 1/6. And so you could see the relationship between the trial and the exponent associated with the probability of failure is that there's a difference of 1. All right, so if n represents the number of trials, then n minus 1 will get you your exponent. All right, so that's where this comes from. 5 over 6 to the n minus 1 times the 1/6. All right, and that's something you could graph. Since we're working with discrete cases, it's kind of tricky to go that route. Yeah, so if you wanted to do it in like the function grapher, that might be a problem. The better way to do it is to just use a statistical, statistical method, so a list. All right, so I'll show you real quick. Under statistics, I gotta get in there before I can actually delete the data. I have 5 values here, so I won't use a rule. Thank you. I'll just add a few more cases to it. So I'll go 6. I'll go up to 10. Oops. And then for my frequency column, clear that out. Just making sure it's not going to wipe out what I just typed in. Okay. It didn't really matter because I'm going to go with fill with a formula. And so in this instance, I don't have to go for something fancy that I might find in the toolbox. It's a pretty simple formula, and in fact, I could have even asked you questions like this in the last half of the unit where I'd say, you roll a die 7 times, what's the probability that you only get, actually I might have asked that on the test. Yeah, I think it was like, what was the probability that the only question you got right on the test, on the multiple choice quiz was the last one, was the first, it's kind of a play off of this idea. All right, so 5 over 6 raised to the, where's my raised to the, V1 minus 1. So shift alpha V1 minus 1 multiplied, I'll put a multiplication symbol in there. I don't think I need it, but different platforms go about it different ways, and I don't want to take a chance. All right, so V1 is the exponent, V1 minus 1 is the exponent because we're taking whatever the values, and I do have to make an adjustment. Now I just realized it. See if I can, nope. No, I'm gonna have to type it in again. I just realized I have a 0 in my first column, so in V1, so that would be a problem. Just quit out of there. I just got to delete that one out, and then do it. With the handhelds, I can highlight, copy, paste, but with the app, it doesn't work quite as nicely. All right, so 5 over 6 raised to the shift alpha division. Oh, it didn't raise to the, because I didn't actually hit the button. Shift alpha V1 minus 1, and then 1 over 6. Close it up. I'll put that little multiplication symbol in there. And boom. All right. And you could see, just looking at the probabilities, it's declining as you increase your number of trials. So the probability of success is 1 out of 6. So you should be kind of living in the neighborhood of low numbers, anywhere from 0 to 6, maybe even 0 to like 8 or 10, before you get your first success. If the probability is 1 over 6, the expected number of values, number of trials that you take before you got your first success would be 6. Right? You just think about it like, I roll a die 6 times, I would hope that I'd get each outcome over those first 6 times. We know it doesn't work that way, but that's what I would expect. All right? But we could also take a look at the graph. I have another one enabled, so let me get rid of that. I never remember to turn it off. Histogram. You can see it's a declining graph, but it was already in the notes, so you knew that. That's not anything earth-shattering. But you could also get an idea of what the mean ought to be. All right? as you increase your number of trials, you get closer and closer to the true framework of whatever the experiment is. Right? So I only went out to 10 values, so it came back with a mean of 4 and change and standard deviation of 2. But if I went out 100 values, which with the NumWorks calculator we know that that's the max, it would tend towards its true mean. Right? And that mean is determined by 1 over whatever the probability of success is. All right, so I'll just make a note of it here because it's kind of buried in the notes. But the mean, mu, is equal to 1 over p. And that's true in all cases. All right, if you had infinitely many trials, or for statistics, anything in the discrete sense, we would say a very, very, very large number of trials, the probability would dictate where the mean is going. The mean would be going to the inverse, well, in this case reciprocal, it's a form of an inverse, but of the probability. Right? So, it's kind of like roulette, trolley game. Spin the wheel, there's 38 possible outcomes. If you spin it 38 times, and you're hoping that, like, I want the number 7 to come up, if 38 spins of the wheel, by the time you get to the 38th spin, you're at your best probability of having gotten at least 1 7. Right? But if you look at this in the way geometric distributions work, is we have our sample space 1 through 6 for die, really 00 through 36 for roulette trolley game. If you look at it as many sets of 6 trials, that's kind of a better way to do it. It's got a central limit theorem feel to it, and we'll get to the central limit theorem for this stuff down the line. But yeah, that's the general idea. The variance, I went with the less popular notation. This really should, if you want to put it in a form that you're more familiar with, this would be sigma squared is equal to 1 minus p over p squared. All right, so for large sample sizes or small sample sizes repeated over and over again many times, compiled into a single large sample size, the mean should be 1 over p. The variance, the population variance, should be 1 minus p over p squared. But if you're looking at just the population standard deviation, you would say the root of 1 minus p, and that would be the principal root, because you would plus or minus it anyway to make the distribution out of it. So the square root of 1 minus p over p. All right. So if
Is it like the square root 1 minus p over p, the square root of that, or like the square root of 1 minus p all over p?
All over p, yeah. So on the fly, I took the square root of p squared. So this became this. All right. So let's say, for example, I want the probability, I'll say, I'll go back to the basketball player. Basketball player typically makes 90% of his free throws. I know there's some version of this packet where I actually have this example. All right, so if I wanted to find the probability that the first success is on the 7th attempt. When I say something is common sense, I tend to worry that somebody's gonna be like, well, I don't understand this, I don't know how the heck is common sense. But this is one of those cases where, I don't know that you would have needed this lesson in order to figure it out. There are some behind the scenes stuff that you'd have to verify. So first, it would be, is there a fixed number of trials? Yes, it's binomial. No, it's geometric. right? It's a fixed number of trials. So it's the same list. Fixed probability, independent events, 2 outcomes. All right, so for fixed number of trials, we would say no, because just because we're stopping the experiment at the 7th attempt to see what's going on doesn't mean that this couldn't go on forever. I mean, we don't have a set number of attempts. Right? You might have a practical set number of attempts, but then you're getting specific to the game of basketball. Like a good basketball player typically will take 12 free throws during a game, you know, something like that. We can't make that assumption. Right? Fixed probability, we're assuming that. In fact, we're assuming all these remaining things just based off of the nature of basketball. Independent events, you know, like you miss 3 free throws in a row, you're starting to wonder if you're ever going to make one. Or the other approach is like, let's go with like 3-pointers. You just made 3 consecutive 3-pointers. So the next time you jog down the course, you hoist the court, you hoist one up because you're like, I'm on fire. You know, like how you performed before has impacted how you continue to play. And also 2 outcomes. That's kind of a weird one, but you could define success in basketball as in a variety of different ways. So we don't really truly know it's binomial, but in terms of the 2 possible outcomes, but these would all be the assumptions that we would make. All right, so that gives us license to use the geometric distribution. All right, and again, it's because we have 1 no, specifically the fixed number of trials, but everything else is a yes. All right. Now, using the formula, pretty easy. I missed it 6 times in order for the first successful attempt to be the 7th time. So I'd say 0.1 to the 6th, 0.9. You could say to the first, but I wouldn't. All right. Now, I would kind of chuck this in the category of probably the least useful tools on the calculator in terms of simple computations. But if you go into the toolbox, you'll see geometric, and you have P x equals m, where x follows the G distribution. The P is generally and almost always going to stand for probability. So if I select this, right, number of the first success would be on the 7th trial, and the probability of success, it gives you that number. So then 0.1 raised to the 6th times 0.9 gives you that same number. All right, so you could use Geom PDF 7 and 0.9. This would be the first success, and this would be the probability of success. I think my pen is about to crap out. Which is perfectly timed because that's really it for this lesson. All right. So we're just applying what we already know, but in a different way. And you know, geometric distributions are a lot easier to handle in terms of the computation than something like a binomial distribution, because since there's only 1 success and it has to be in the last attempt, there's no concern about different combinations of getting one success. I mean, if the question was find the probability that out of 10 free throws, the individual only makes 1 shot, then it could be the first shot, it could be the second, it could be the third. We care about where it falls in that distribution. But here we know where it's going to fall. It's got to be the very last one. All right. So, like I said, that's the lesson.